Hello. I try to be short. This the work we make with this sub-project. The nice thing of the work is it was a mainly conclusion for all the comparison we make between the Regional Brewer Calibration Center and the World and Regional Dobson Calibration Center with the collaboration of René with his data from Arosa and Martin Weber from the Bremen University who provides the ozone cross-section. I will start with a short introduction. We show the methodology for the calculation for the ozone cross-section for Dobson and Brewer. And we concentrate in the current ozone cross-section we use in Dobson and Brewer, the result for the operative temperature. And then we analyze the temperature dependence that in both algorithms, Brewer and Dobson, is not taken into account. And finally, we apply all this study to real data in the reference instrument comparison. At Designa, we show something in my previous talk, and finally with the Arosa time series. So I can skip. Everybody knows the Dobson and the Brewer. But I want to say that since the beginning, there was an initial difference of 4% between Dobson and unit, Dobson and Brewer. When we introduced the same cross-section, the mass and power, this part of the 4% was greatly reduced. So the initial difference between Dobson and Brewer was also due they used different cross-section at that time. When we have a Brewer and you have a Dobson in the same place, he always shows some seasonal dependence between both data for many years. There was an attempt to explain that mainly for empirical correction, statistical correction, but in this work we want to show that the reason of this seasonal dependence is due to the different response of the Brewer and the Dobson algorithm to the stratospheric temperature. We use 5 ozone cross-section datasets, 3 mass and power. The reason to have 3 mass and power because Dobson, Brewer, and the proposal for the satellite use different mass and power version of the same data. And the Damon-Baliset-Brion is the set that the NASA suggests to use for the TOMS evaluation of the ozone. And finally, the new measurement for the University of Bremen. The ozone absorption coefficient for Brewer and Dobson are calculated using the Brewer operative method. Dobson and Brewer, as I said before, using a fixed temperature, so they don't take into account changes in effective temperature of the ozone layer. I can be fast for that. Everybody knows how we calculate the ozone. And when you expand, all the coefficients are really weighting for the select function of the cross-section. And we use a simple method. Just this is the slit of the instrument. This is the cross-section, and what we call the absorption coefficient is the integrate of that. And the main difference that the Dobson assume all the instrument has the same slit. This is not real, but for the Dobson, everybody has the same slit function like he measured in '83. And for the Brewer network, every instrument has measurement slit during the dispersion calibration and with the slit and central wavelength, and we determine every calibration for that. This is an example for the 5 cross-section we analyze. You see in this plot, they are one over the other. They are different resolution, but you don't see changes. But when you look in the tail, this is a slit for the Brewer, this is a slit for the Dobson, you start to see changes that will affect, we have different results when we apply this integration of the cross-section. I already skipped that. To see the difference between the calculation, I plotted here the cross-section and interpolated in a common resolution and smooth for the Brewer slit resolution. So now it's more clear how different are the different cross-section. Even the same mass and power, you have here the operative from the Brewer, the exact value -45. This is the Bernhard cross section. This is Bazan power, but it takes into account a standard atmosphere and all this calculation, the amount, and the new the Bremen University. You have two versions. One because they don't have measurements at minus 45. This is the linear interpolation for that temperature, and this is the quadratic interpolation for that temperature. You have a slightly different result for that. So when we apply this method to the Dobson, the main value is that the pair change is 1%. When we compare with previous calculation, the agreement is quite good. So with when compare the values with the value obtained by Bernhard in 2005, the results are the same. And this is the Brewer calculation. We use the data set for the different campaigns, and you can see here the variability between the instruments in the ozone cross-section. And every family has a difference. You can see here that if you have a change in one cross-section, it's mirrored in the others. So we can use this fact to analyze space data. So you have this difference will be proportional to the difference between the operating wavelengths to a standard. I call the Brewer one here is not the Brewer one, it's the average of all the Brewers I have. So this difference will be proportional to the difference between your wavelength in this particular Brewer to the Brewer average, the Brewer one. So when we apply this calculation, we see that the EUP changes the ozone very, very low, 0.5. If we use the quadratic calculation, it's increased a little to almost 1%. And this is what we find in this AXO meeting, that the amount is terrible effect to the Dobson series because we have to be below 3% all the Brewer data. And finally, this is also a very surprising result for me. The R3 version of the Bazan Pau, if I use, they propose the Bazan Pau who is used by NASA for the ozone retrieval, I get a difference of 1.3% in the same Bazan Pau cross-section. So it's really amazing how dependent is the ozone calculation for the Brewer for the cross-section. We can compare these values with different determination from Sebastiuk in the ASCO campaign, and we have almost the same value, except Escarnato work. We cannot reproduce his calculation. Also, he was doing a sauna with Alexander, and this was a determination at Izaña. When we introduce the temperature, we use a simple approach from since Commit 93 we use for the Dobson. We assume that we can estimate the temperature by a vertical profile for an effective temperature. This temperature is just a convolution of the ozone through the temperature profile, and we use this this assumption. So first, the temperature can be in the cross-section can be approximated by the quadratic polynomial, and the second, the temperature ozone profile will be simplified by introducing an effective temperature. Then you can derive the calculation, and finally, you can express the temperature dependence as a gradient of the cross-section. When we plot this gradient, you can compare here the different colors are the different cross-section, and the circles are the Brewer, without circles are the Dobson. As you can see, the Bremen cross-section, the effect is quite flat in the Brewer. It's really, really flat. They have any temperature dependence. The effect in the Dobson is bigger. If we use the Bazan power, you have a big slope, and if you use the amount, the slope is opposite. It's not so big, but it's the opposite. So we can compare with previous calculation for this. So and again, we can reproduce mostly of the different studies, except with the Scarnato, he made the calculation with the Arosa brewers. When we apply this to real data, I saw it yesterday, so I will skip this plot. So it's the Brewer and Dobson calculation. But again, when we use to remember the Bremen cross-section, the difference between Brewer and Dobson completely disappear. At Isanya, we cannot look at the temperature effect because here the effective temperature doesn't change during the year too much, only 5 degrees. And this was the data for one campaign, so the temperature doesn't change. That was very similar to the temperature that was assumed for both algorithms. So we go directly to the Arosa. So we analyzed 3 years of observation from Dobson and Brewer, one single brewer and one double brewer. Dobson and Brewer were corrected using the temperature from Payen ozone zones, the effective temperature for Payen ozone zone. We tested, because we have the ozone zones once a week, we test several methods of interpolate this effective temperature, and we don't find any difference between different using the same coincident data, or you interpolate linear, or you doesn't affect significantly to the results. And then we investigate the set to the real data from this brewer, and also for a generic brewer, to see how can extrapolate this value to other stations. And we found also we don't have any significant effect. I repeat this value with the real data to the real to an average brewer. Here you have the difference between Brewer and Dobson for these 3 years. The points are the effective temperature, and you have the single and double brewer. As you see, the temperature is anti-correlated with the difference. And then when we apply this temperature correction with this data, we see first, when we apply to Damont reduced completely the seasonality. You have the effect of the 3% we see in the absolute value, but also the seasonality is completely disappeared. Here you have the temperature, and then when we see in previous study for Scarnato, you have this effect when you use the Basan power. And then when you apply the new cross-section, this completely flat. So it's also disappeared. You have the effect of the scale of 1%, 0.9% we see before. And the difference between the dots and the line is the double and single brewer. You don't have significant effects except a different change of calibration between both instruments. So we conclude that the Brewer and Dobson instrument results are grouped best when we use absorption coefficient based on Bremen cross-section. The application of the temperature dependence absorption coefficient substantially reduce the difference between Brewer and Dobson at Arosa. This temperature depends values obtained here confirmed the hypothesis of Kerr in 2002 that the systematic annual difference between Brewer and Dobson are due different temperature dependence in the instruments. And also confirmed that they say that the temperature dependence in the Brewer is very low. The Dobson record will change less than 1% if we don't take into account the temperature. And a change of the temperature provide the most benefit to remove this artificial seasonality in the Dobson records. If we apply how to correct the past Dobson data is another issue, because you don't have usually ozone zones near. You don't know if it's better to use climatology. You are introducing some artifacts in that, so it's really an issue for the next year how to improve the Dobson data for that. The calculation of cross-section for a particular brewer is very sensitive, both to the cross-section and the handling of the cross-section. with these 3 Boston power, sometimes the only difference is just smoothing, or they have removed some points, and you see big effect into the results, and can be as large as 1%, only for the handling of the data. The Brewer record can be adjusted to the, let's say, Bremen scale using past calibration, based in the uncertainty of this campaign, or all the instruments of the campaign. If you use an average brewer, you can go, your error can be as far as 0.4%. If you know your operational wavelengths for your brewer, you can estimate the change and the uncertainty is reduced to 0.1%. Ozone profile measurements as well the climatology are now evaluated to estimate the effect in Dobson. And for these are no conclusions for my work, this is a conclusion for the meeting of the ASCO. One of the conclusions, we need a new version of the harmonics of the Bremen cross-section to estimate the error we have in this assumption of quadratic parameters. And also we need this to estimate the budget of this assumption inside the Brewer algorithm. Most of the things will we take into account in this Atmos problem we started in October, this coordinated by the Julian Grobner. So with this project, we characterize Brewer, Dobson, and Pandora instrument in meteorological facilities using this nice stuff like a climate chamber, tunneling laser, and determine the starlight not only with one wavelength, try to measure in all the wavelengths, and also to estimate the error budget in the ozone measurement. For this project, is also participate the Bremen University, and his topic is to provide a specific set for ground-based measurements in this range, 300 to 330, to see when we estimate the error budget, to see how we improve that. This is the master slide. Thank you very much.